Everyone. This is section 4.4, linear correlation. Now we're still going to use the data that we got in the calculator to be able to do this section. You're just going to have to interpret the data, so hopefully you're getting a grasp on how to enter this into the calculator. So what is linear correlation coefficient? Well, this is this measures the straight line relationship between two quantities. For instance, you might measure study time versus score on a test. And if that has a positive relationship, they would all be increasing, right? So this is our linear correlation coefficient. It will help us determine that strength and direction. Now it's also called the Pearson product moment correlation coefficient, but that is quite long to say, and so you'll hear me say linear correlation coefficient, or just correlation sometimes. Alright, so it's important that you understand the characteristics of R. Now R reflects the slope of the scatter plot. So if you have a negative R, you've got a negatively sloped scatter plot. Your line of regression would be negatively sloped. The sine of R and the sine of the slope of the regression line are going to be the same. Now R will tell you what kind of, or suggest I should say, sometimes it doesn't tell you, so we have to say suggest. Now I'll explain more about that later. It suggests the type of linear relationship. Now the magnitude of R indicates how strong the relationship is. Now the magnitude would be like taking the absolute value of it, okay? So here's our examples of what R can look like. Okay, R will be between 1 and -1 usually, and R is, the closer it is to 1, the closer it is to -1. That's actually a good thing, because that means it has a perfect positive or a perfect negative correlation, depending on which one it's closer to. Now the closer we get to 0, from both directions, the positive and the negative, the less correlation, the less strong our correlation is. And 0 has absolutely no correlation. Okay, it's just scattered about. Notice how these other ones are pretty much scattered about a line. Okay, so, and as you start getting closer to 0, the more scattered the data gets. So this kind of tells you that the stronger the correlation, the more the data is grouped along that line. So this is our same problem that we've been using now what seems like forever. We used it in 4.2 and in 4.3. But this time we're going to use that data to help us find out the linear correlation coefficient, or R. Okay, so let's pull up our calculator. And here's our calculator. And with it, hopefully you already have the data in your calculator, because hopefully you're watching all of these at one time. And so here's our data. If not, feel free to pause it right now and copy that down in your calculator. But if you do, we can go ahead and start the process. So stat over to calc, down to linear regression, mash enter. But remember, our data is typed in L1 and L2, so second L1, comma, second L2, and mash enter. And we've been given our data. Now, just like before, we were given the regression equation, and we were given R squared. Now, what was R squared? This is a good review for you. R squared was the coefficient of determination. And what does the coefficient of determination tell us? It tells us how useful the problem, the equation is. And because 0.85 is very close to 1, we can determine that this equation is going to be very useful. The closer to 1, the more useful it is. Now, the last variable up here is R. This is our linear correlation coefficient. So R is 0.92 here. So I didn't want to do that. So R is 0.92 here. So at this point, we can say R equals -0.92. Okay, and it's going to pop up here in a minute. This computer's a little slow today for some reason. Alright, so this is our R. Now that would be your answer for letter A here. Letter B would ask you to interpret this information. What does it mean in terms of the age and price of the Orions? Well, what it means is this, is we have a strong negative relationship here. That's been proven, okay, by R. So what that tells us is this, is that as the age increases, the price decreases. And that should be kind of obvious to you, because I believe if you remember, Orions was a car. So as the age of your car increases, the price decreases. That should be kind of obvious to us. Now, it's also important to note that if you have a strong correlation, like we do here, even though it's negative, we do have a strong correlation. That means you're going to have a strong coefficient of determination as well. So that means that if you have a strong correlation, that our equation will be useful as well. So I'll show you more about that here in a minute. But what are the graphical implications of this? Well, it's close to -1, as we said. So all this data should be clustered together around that line, but around the regression line. And it's going to be in a negative direction, that regression line. It automatically tells you how this data and the regression line is going to be laid out on your paper. It should be in the negative direction. Alright, so the coefficient of determination. How does that relate to our correlation coefficient? Well, our correlation coefficient is R. This is the correlation coefficient. Okay? And for some reason it keeps backing up on me. Alright, this is our correlation. Now, notice it says specifically that the coefficient of determination equals the square of this. So, in other words, R squared equals the coefficient of determination, which we learned that earlier. This is nothing new to us, okay? R squared is the coefficient of determination. So, for instance, we figured out that R was -0.92. Well, if we want to know the coefficient of determination, we can figure out R squared, and if you square -0.92, you're going to get 0.85. And if you go back and look at your data from your calculator, that's exactly what we got. That's exactly what we have on our calculator, if you remember. So, and I forgot my square here. If you square this, okay? If you square this. Now, so whether it's a negative correlation or whether it's positive, a strong one, because we're squaring it, will always give you a strong coefficient of determination. Now notice that second bullet up there. It says the square root of R squared gives the magnitude of R. So I could take the square root of 0.85, and if I take the square root, of 0.85, I'm going to get 0.92. So the square root of 0.85 equals 0.92. Now that's why it's the magnitude. Notice it says it's the magnitude. The reason it's the magnitude is because notice that 0.92 is positive. Our correlation is negative. So in order for you to get the correct correlation off of this, if you were trying to take the square root of the coefficient of determination like we did here, and you were trying to figure out what the correlation was, you would have to know the slope of the regression line. And we do. We found this regression equation a long time ago, so you can look in your calculator and find it. The slope of that line was negative. So because the slope is negative, we automatically know that R, or our correlation coefficient, will be negative as well, because the regression is negative. So that's how you're going to have to do that. If you're going from coefficient of determination, take the square root, but look at your regression line and make sure you know what the slope, the sign of the slope is, so that you can make that sign one and the same, okay? So you can make that sign one and the same. Now, some warnings for R. R should only be used as a descriptive measure that tells you how the points are scattered about a line, okay? It's not to be it's not to say anything other than that, because there can be a lot of misconstrued opinions about R. It's just telling you how those points are scattered about a line. But you got to watch for outliers and influential observation, because they can sometimes affect R, because sample means and sample standard deviations are not resistant to outliers and other extreme values, okay? So, correlation and causation. This is the important part. This is the part you're going to want to make sure that you remember, is that simply because you have a strong correlation, that doesn't mean necessarily that they caused each other. If I say that Mountain Dew intake is strongly correlated to a hurricane, that doesn't necessarily mean the hurricane caused the Mountain Dew intake. Does that make sense? Two things could, with data the way it is, with variables the way they are, two things could be correlated and have a strong correlation and not be linked in terms of causing one another. And the reason of that is because we have things called lurking variables. There are some other variables that cause the correlation to be very strong, okay? So you may have a lurking variable out there. So be careful in assuming that correlation and causation are equal, because it just doesn't imply that all the time, okay? So take that into consideration as you're going through this lesson. Now, make sure that you're getting familiar with your calculator, and as you begin to have a few questions and work in the homework, please feel free to ask your instructor. They'll be glad to help you. Have a great day.